So I'm going to be starting with defining what is computational complexity and why is that important. Anybody who is going to do things by computers, they have to understand the basic principles of computational complexity. Okay? So let's assume I have an ideal computer. In a practical computer, the word length is limited to 32 bits. In a practical machine with 32 bits, you can only represent numbers up, real numbers up to 5 to 6 decimal accuracy. All of it may? Do you all know that? That's right. But real numbers, for example, 1/3, it is a repeating expansion, 0.33333. No matter where you chop, you are going to make an error. The number pi, I don't know how many of you know, one of the standard mathematical open problem is the decimal expansion for pi. What is the pi value we take? 3.12, but it's very approximate result. Ramanujan has given several formula for computing pi. And using the formulas that Ramanujan had given, people have used those formulas to compute the number of digits in the decimal expansion of pi. And what is the major open question? We still don't know whether the decimal expansion for pi either terminates or does not. What is my terminating expansion? 1/2, 0.5. 1/3, non-terminating. So some real numbers have terminating expansion, some real numbers have a non-terminating expansion. There are lots of numbers we need. E, the Neperian base. What is the value of the Neperian base? 2.67. Is it 2.67? Very approximate, very good approximation. What is pi? 3.12. What is the charge of an electron? What is the Avogadro number? Are you back? Come on, guys. So in physics, they worry up to 14 decimals. So in most of the problems in physics, especially in atomic physics, they do in double precision arithmetic. In double precision arithmetic, the word length is 64. Single precision arithmetic, the word length is 32. In double precision, you can do up to 14 decimals. In single precision, you can do only up to 6 decimals. So what does that tell you? When you are going to add, subtract, multiply numbers, you can never do it exactly. I'm going to give you an example. That's where I'm going to start. Suppose I have a machine where I can represent real numbers up to 3 digits. It's an ideal machine, right? Good. So I have an EA is equal to 0.672. I have a number B, which is equal to 5.79. Three-digit numbers. I want to add. So in here, how do I represent my numbers? My number is represented by plus or minus 0.m1, m2, m3 times e1, e2. That's called. So a number can have a sign. It is given up to 3 digits. It is an exponential times that. The exponent can have a plus sign or minus sign. So I need to represent these. I need to represent these. So I'm going to. So I have stored this in my computer. You say load A, load B, add. If I added them, what is A plus B, which is equal to C, which is equal to 9 plus 2 is 11. 8 plus 7 is 15. 1, this is 12. When I want to store this, the computer will not take this. I have to convert this into this form. So this is equal to plus 0.1251 times 10 to the power of 1. The computer will say, hey, not that fast, stop. I can't take more than 3 digits. You have given 4-digit number. So when you store it, so at the accumulator, you get the real value. When you store it, you can store it only like 0.125 times 10 to the power of 1. There's an error. Everybody with me, please?
Yes.
So whenever you do an addition, there is an error. When you do subtraction, there is an error. When you do multiplication, there is an error. When you do division, you are an error. It is not that I don't know how to divide. It's simply that the computer cannot store it. Therefore, arithmetic in finite precision arithmetic. What is finite precision arithmetic? The arithmetic implemented in a machine. There is always an error. The results are only approximate. That's the first fact. Second fact. Time to multiply is more than time to add. Are you with me?
Yes.
That's right. Hey, that's the reason why we learn addition first. Then we learn subtraction. To learn subtraction, you need to be able to borrow. Borrowing is not an easy concept when you are teaching a child, 3-year-old, 4-year-old. So you first teach addition, then borrowing. Borrowing means what? Importance of positional number system. Yeah, 1 here is 1. Yeah, 1 from here is 10. Yeah, 1 here is 100. So when you are trying to teach subtraction to young children, you are trying to implement the idea of a positional number system. You are trying to impart that knowledge of a positional number system. Once you know addition and subtraction, then you know multiplication. Then you do division. Division is longhand. So division and multiplication are more expensive. Philosophically, addition and subtraction are essentially the same. In different, whether you do it manually or different computers, division takes more time than, multiplication, division takes more time, addition and subtraction. So computer scientists, they created what's called an ideal computer. So what is an ideal computer? In an ideal computer, I don't want to be bothered by the round of errors like this. In an ideal computer, I don't want to be bothered by the difference between the time required to multiply and add. So what is an ideal machine that computer scientists, theoretical computer scientists have tried to model? So what is the model of an ideal computer? So there is a real computer, there's a model of an ideal computer. What is the model of an ideal computer? In an ideal computer, each word length is infinite. There are infinitely many such infinitely long words. Why? If the word lengths are infinite, there is no round of error. If the infinitely many such words are there, I have no depth for memory. I'm not going to be concerned with the memory. Let there be space, and there it is. All of it, me? That's right. And then what? We are going to assume the time to multiply, the time to add, time to subtract, time to divide, they're all the same, equal to 1 unit. Even though in practice, multiplication takes more time than additions. Are you with me? Yes. So that's called an ideal machine. The ideal machine is called unit cost machine. Every operation costs only 1 unit. I'm not worried about the length or the size of the unit. So in practice, what is that you can do? In the actual machine, there is a time to multiply, there is a time to add, there is a time to subtract. You can take the maximum of those to be the unit. If I took the maximum of all those to be the unit, then every operation can be done within that time. All with me, please? Yes. So the starting point for computational complexity is I don't want to mess with round of errors. I don't want to mess with the lack of memory. I don't want to mess with the differences between addition, multiplication, subtraction, division. So I'm going to be not bothered by all these things when I am trying to do the analysis. In real world, these things have to be taken into account, but I'm not going to be requiring to find the exact time. I'm going to estimate the time. Will it take 3 hours or 3 days? That's the question you're going to ask. So given a particular problem, I want to get a decent bound on the time required to solve the problem. And this bound I'm going to derive on my abstract theoretical machine. Are you all with me now? What the theoretical computer is all about? It is a replica of the real computer, except that I have made some adjustments. One more. In a real computer, if you want to store, that takes time. If you want to load, that takes time. So in my ideal computer, I'm going to assume my store, load, all these operations are instantaneous. Let there be light, and there it is. Okay. So the load store time is 0. All the time for every operation is unity. I'm not worried about the length of the unit. So if every operation is going to take unit time, if I have a problem of size n, I'm going to represent my time equal to in terms of the number of basic operations. So what are the basic operations? Addition, multiplication, subtraction, division, comparison. That's it. So if you give me a problem, if you give me an algorithm, how do I estimate the time? It is the sum total of the number of addition, multiplication, subtraction, division, comparison, assuming each one take 1 unit of time. So the time is measured not in terms of the clock time, hours and minutes, but in terms of the number of basic operations. Why? If I measure the time in terms of clock time, some computers are faster than others. It depends on the hardware. Given the same problem, given the same algorithm, no two of us code the same way. Some people code it intelligently, some people do it in a long way. Okay? That's right. So it depends on the programmer. It depends on the compiler. It depends on the quality of the compiler. So if I'm trying to quantify the time to solve a particular problem, it should be independent of the machine, programmer, compiler, language, operating system, and everything else. Then I will have an abstract representation of the amount of work to be done to solve a particular problem. So to me, the work is the number of operations. Each operation is going to take unit time, so the time is also equal to 1. So in computer science, it is conventional to be able to quantify the time required to solve a particular problem, not in terms of hours, minutes, and seconds, but in terms of the basic total number of basic operations. For example, if I told you I solved the problem in 2 hours, that doesn't tell you how many operations you performed. But if you tell me I have to do 10,000 operations, I can convert the number of operations into seconds very easily if I know the speed of the computer. But if I give you the time, I cannot recover the number of basic operations. All of it, please? Because of these arguments in computer science, we assume I have an ideal computer that's called a unit cost RAM model. Unit cost RAM model. What is RAM? Random access. What's the property of random access? Any part of the memory can be accessed in the same amount of time. Now I have assumed that access time is 0. I can get data from any part of the memory in 0 delay. What is unit cost? I already talked about. So unit cost RAM model is an ideal machine using which I'm going to quantify the time. Time not in terms of hours and seconds, but in terms of number of basic operations. Is that clear to all of you? Come on, guys. Yes. Okay. So with that in mind, if I have a problem P, so let me go back. If I have a problem P, the size of the problem is n. The time complexity is equal to T of n is equal to number of basic operations. I'm going to start by giving some examples now. I'm going to start by giving some examples. With me? Yes. So the Tn is called a time complexity function. The time complexity function depends on 2 things. One, the problem, the algorithm, and n. The same problem can be solved by several algorithms. Each algorithm will have its own time estimate. We need to be able to pick that algorithm whose time estimate is the minimum, the least. All of it? Right. So let's give some quick examples to be able to get this idea across. So if I have two vectors, so let A be two vectors in Rn. I want to be able to compute A transpose B, the inner product. That's equal to summation AI BI, I is equal to 1 to n. So what is the total amount of time required to compute the inner product of two vectors of size n? I have to perform n multiplications. Then I get n numbers. To add two numbers, I need to make one addition. To add three numbers, I need to make two addition. To add n numbers, I need to make n minus one addition. So in principle, I should be able to do with n minus one. Addition is a cumulative process. So how do you write a program to add? S is equal to 0. Do I is equal to 1 to n. S is equal to S plus AI star BI n do. Don't you think this is the way you write it? Come on, guys. Yes. So I'm trying to set the accumulator to 0. I'm going to, for each trip of the do loop, I'm going to make one multiplication, one addition. So in this implementation, there is n multiply, there is n add. However, I could also have rewritten this as S is equal to A1, B1, do I is equal to 2 to n, S is equal to S plus AI, BI, and do. I could have written like this too. All of you? Yes. How many of you with me? Yes. All right. So in this case, I have one multiplication, n minus one multiplication, totally n multiplications, but I'm only doing n minus one addition. So the theoretical n minus one addition, if I want to implement it, I would write this way. I could also write this way. So which one is better? According to software engineering, the right one is better. Whenever you are trying to accumulate a process, always clear the accumulator, start with 0. That's a good practice. What is the cost? One more addition. Never mind. When n is very large, n minus 1 and n, they don't differ too much. So when you write programs, your program must be usable by several people. The program must be as error-free, as readable as possible. So therefore, this way of implementing is better than this way of implementing. That's called good software engineering practices in computer science. So with that in mind, now you can readily see if this is not n minus 1 add, this is n add. Therefore, the inner products can be computed in time is equal to 2n. Everybody? 2n is a linear function. Therefore, the complexity of inner product is a linear function in the size of the problem. How many of you know? Yes. Now let's consider the outer product. We saw the need for outer product in the last class. Do you remember? Yes. Hello? Yes. That's right. So if I have A, B transpose, that is going to be a matrix, which is AI, Bj, 1 less than equal to n, 1 less than j equal to n. So it's a n by n matrix. I goes from 1 to n, j goes from 1 to n. I have to compute n square elements. Each element can be computed by one multiplication. So in this particular case, Tn is equal to n square. The quadratic complexity. N square grows faster than 2n. Are you with me? Yes. That's right. Now let's go to matrix vector computation. One by one, one by one. I'm going to quickly talk about some of these things because these are fundamental. So if I am going to compute y is equal to ax, a is the matrix, b is a vector, and y is a vector. So what does this mean? This is that. So if I consider yi, I consider the ith row, I consider the vector x. So what is yi? Yi is equal to summation aij xj, j is equal to 1 to n. Everybody knows that. So every element is an inner product. Each inner product takes 2n time. Therefore, the total amount of time required to compute y is 2n times the n, which is equal to 2n squared, and that is TFN. The matrix vector product is twice as expensive as the outer product. Outer product is quadratic, matrix product is quadratic. Inner product is linear. So if you are considering large problems, matrix vector is going to take too much time because I'm square. Are you with me? Now let's do matrix product. C is equal to AB. This is C. This is A. This is B. This is Cij. So to compute Cij, I have to take the inner product of ith row of A and jth column of B. So Cij is equal to summation Aik Bkj, k is equal to 1 to n. I'm sure you all know that. So this is the inner product. So each element of the result can be obtained by an inner product. Each inner product is going to take 2n time. How many Cj's are there? N squared. How many of me? There are n square elements in C. Therefore, what is the time? 2n times n squared, which is equal to 2n cubed. Wow. Matrix multiplication, the cost is cubic. How many of you know this area? That's right, we are learning now. So when you write a program, you write various instructions. You have to worry about how much cost each instruction is going to incur and what is the total cost. So what does this tell you? Avoid matrix multiplication whenever you can, wherever you can. You do matrix multiplication unless that's what you want to do. Now the next question is, I want to solve a linear system, X is equal to B. So X is equal to A inverse B. How many of you know methods for computing A inverse B? Gaussian elimination. That's n cubed. How much time does it take to compute the determinant? It's a homework problem for you to think. How much time does it take to compute eigenvalues? How much time it takes to compute the trace? How much time does it take to compute eigenvectors and eigenvalues? How much time does it take to solve an ordinary differential equation? How much time does it take to solve a partial differential equation using a particular finite difference scheme? Are you all with me? When you guys talk about model, that's what you are doing. How many of you have written codes for the model from ground up? How many of you use models? Who wrote the model? That's nothing wrong. I want you to understand. You are trying to use the product somebody else did. There's nothing wrong with it. You don't design the car, but you buy a car and drive. You don't grow vegetables. You buy the vegetable, but eat and enjoy. You don't write the code, but you use the code that somebody else wrote and you do make some improvements and make your theory. There's nothing wrong in that. So I'm not trying to find fault with you. Please don't mistake. If you want to grow your own rice, your own vegetable, your own everything, you won't live here, right? That's right. So that's why there are agriculturists, there are farmers, there are professors, there are everything else. So we all have to do our thing to be able to do things. Now let's have you ever thought of how much time your model is going to take? You'll only come and say, hey, my model is taking too much time, I don't know why. Are you with me? Yes. That's right. So what is the first task for you? If you are going to be doing coding, either you do it yourself or if you use somebody else's code, please print one copy of the entire code. You should know what the code is. If suppose somebody comes to your tray and then say, do you want to eat this? What's the first question you ask? What is this? That goes into my mouth. Don't you ask that question? I hope you do. You don't eat anything that comes your way. So what is the first thing I want you to do? Know thy model. I want you to print at least one copy and have it here and understand the whole structure of the model. Understand the mathematical equations, understand the code, and be able to see which part of the code corresponds to what part of mathematics. Please do. If you did it, nobody can touch you. You become a master of the trade. All of you? Why is this needed? Because in order to be able to understand the time it takes to run a code is fundamental to problem solve. Let me give you an example now. IMD, they are interested in 24-hour forecast. How much time they have to be able to create a forecast? They collect the data through the day. They have to assimilate the data. They have to create a forecast. All the things must be done within 24 hours. Data collection probably takes 10 hours. Data cleaning probably takes 2-3 hours. Assimilation, they will say, you have to assimilate in no more than 5 hours. I'm not going to give you any more time. So they will say, this is the computer given to you. This is the amount of data. This is the model. Please assimilate the data and give me the prediction. So what is that you need to worry about? What is the largest problem I can solve in this machine in 6 hours? Are you there? Yes. In a class, you say, well, I couldn't study yesterday, so please, I need 2 more days to solve the homework problem, right? But IMD people, they cannot say, well, yesterday I did not have sleep, I could not run the model. They have to produce forecast every day. And you have only 6 hours. So 6 hours time, a computer of a given power, a problem of a given size. So you have to ask yourself, what is the largest problem yen I can solve? Are you with me, please? Yes. Did somebody tell you yesterday that my grid is 12.5 kilometers? Come on, guys. Yes. Why 12.5? If I make it 2, I would like it to make it 2. The size of the problem is so big, it will take 3 days to solve. I will lose my job because they give me only 6 hours to produce the forecast. Are you all with me now? Yes. Now, do you see how computer science come into the picture? Do you see how the complexity issues come into the picture? Come on, guys. Yes. That's right. That's right. And that's what I'm leading to. That's what I'm leading to. So computational complexity is absolutely important, especially in problems where you are going to have to do online prediction. I'm designing an airplane, doesn't matter, I can take 2 days. I'm designing an automobile, I can take 3 days, no problem. I'm designing a nuclear power plant, 7 days, no problem. I have to generate a forecast every 24 hours. I don't have more than 6 hours. Everybody? Yes. So some of the problems that IMD people are facing are the toughest problem. They have to satisfy the public, they have to satisfy the largest problem, and they have the procedure has to be accurate. And people always blame IMD, don't they? Oh God, they said it's going to rain. No, I took the umbrella, there's no rain. These guys, they don't know what they're doing. Everybody? Yes. a tough business. So in that tough business, I want you to be able to understand the whole story. And one of the biggest chunk in the story is complexity. So now I'm going to tell you how much time can it take to be able to do the computation of matrix multiplication. Again, I want you to be able to. So let's suppose I have two matrices A and B, each of size n, and n is equal to 10 to the power of 6. 10 to the power of 6 is a million. I want to multiply 2 million by million matrices. How much time is it going to take? Somebody give their calculator out, please. Does anyone have a calculator? Your computer, your phone can do calculations? Yes. Yeah, okay, get that calculator out for me. So to be able to multiply two matrices, I have to do n2n cube operation. N is a million, so this is 2 times 10 to the power of 6 cube. This is 2 times 10 to the power of 18. Because it is 2 times 10 to the power of 18, I don't have to worry about 2. I will simply take 10 to the power of 18 and then I can multiply by 2. So to multiply two matrices of size million by million, I have to perform 10 to the power of 18 operations. Let's assume I have a teraflop machine. What's a teraflop machine? It can perform 10 to the power of 12 operations in 1 second. Teraflop machine. That means 10 to the power of 12 ops per second. So what is the time required? The time required is 10 to the power of 18 divided by 10 to the power of 12, which is equal to 10 to the power of 6 seconds. I need million seconds. And how long is million seconds? Let's calculate that. There are 60 seconds in a minute, there are 60 minutes in an hour, there are 24 hours in a day. So let's calculate how many seconds are there in a day. Please calculate that. 60 times 60 times 24.
86,000.
Say that one by one. Play.
86,400.
Louder.
86,400.
400.
10 power.
Is that right? Is that what it is? Good. So which is 0.864 times 10 to the power of 1, 2, 3, 1, 2, 3, 4, 5.
11.
5. Are there? So now, so this is equal to 10 to the power of 6 divided by 0.864 times 10 to the power of 5 days. And what is that? That's equal to 10 divided by 0.864. What is that number, sir?
11 point.
10 divided by 0.864.
557.
I
Well, James.
want to engage him.
10 divided by
What that?
10 divided by
0.8. Look at that. Don't ask me.
11.5 seconds. 11.574.
11.
11.57407.
Can I make it 12?
Yeah.
Can I make it 12?
Yeah.
I hope nobody will complain, yeah? So what does it mean? It's going to take 12 days. Are you with me?
Yes.
Just to multiply 2 million by million matrices on a teraflop machine is going to take 11.5 days. You won't have a job in IMD. Are you with me?
Yes.
That is the thing I want you to be able to appreciate. Do you have a teraflop machine here? So even on a teraflop machine, in 6 hours, there's the maximum size you can solve. And that's going to restrict your grid level. So on one hand, we complain that grid is too much. On the other hand, the government doesn't give you larger computers. So who you can blame? You can always blame the government. The government doesn't give me better computers, larger, better powerful computers. I'm going to do with only this. You can always blame the committee, right? You can always blame the government, right? You can't blame a person, but you can blame a committee. You can't blame anybody, but you can blame a government. We continue to blame the committees and government. We don't want to take responsibility. But ultimately, somebody has to take responsibility. and you have to make these time calculations. But the importance of time, the importance of being able to understand every line of a model code, the importance of being able to understand the mathematics and the relation to the code. I want all of you to take a pledge to yourself. I will not run any code until I understand all parts of that code. You make that promise to yourself. Please do. Why? Then you are the expert. Don't you want to be the expert? You need to spend time. And how long does it take? 1 week? You are going to work for 4 years. Do they get you out in 4 years here? 1 week in 4 years is nothing. Even making 2 weeks is nothing. Okay? So know that code, know that complexity. Good. Now, with that in mind, I'm now going to come to my problem. In other words, I want you to be able to understand the importance of time complexity. It is not enough to be able to run the code. It is not enough to run somebody else's code. You need to be able to know every part thereof. You need to be able to quantify the time it requires. Please understand, I'm not trying to belittle the importance of using somebody else's code because somebody has already invested. I want to take advantage of that. Okay? Good. So let's come to the partitional problem. Given n objects, how many ways in which you can partition them into k non-empty subsets? Not the problem. I have been given an object. In k-min clustering, I want to be able to divide the n objects into k clusters. What is k? K itself is ready. And then the number of members in each one can be varying. We have already alluded to that. So theoretically, given a classification problem, how many different ways in which I can classify n objects into k subsets? That's a combinatorial problem. It's like computing the number of permutations of an object. What are the other combinatorial problems? Given 1 to 10, there's factorial 10 permutations, right? How do you generate all the permutations? Given a set of 10 numbers, how do you generate the set of all subsets of a given set? In meteorology, you may not be interested. Computations, they are interested. In computer science, we do that too. Are you with me? But when you are going to be doing clustering, this question becomes very important. So let's give an example. N is 4, K is 2. So in how many different ways in which I can divide 4 objects into 2 subsets? And each subset will be non-empty. So what is the name? If I put all 4 in one subset, the other subset has to be empty. That's not allowed. So every subset can have 1, 2, or 3. How many different ways in which I can divide 4 objects into 2 subsets where none of them are empty? So 1, 2, 3, 4, 1, 4, 2, 3, 1, 3, 4, 2, 2, 3, 4, 1, 1, 2, 3, 2, 1, 3, 2, 4, 1, 4, 2, 3. Everybody? Come on, guys. Yes. All right. So this is the particular. So if you give me a small n, small k, I can do the problem. So what is the general question? Given any n. Now go back to my SAMX ensemble prediction problem. You remember that? I have 25 members. I don't know how many clusters the 25 members ensemble is going to divide them into. So before I start the problem, I just don't know. But if I want to be able to optimally do the problem, okay, I have to exhaust the whole space. To say something, for example, let me give you an answer to this question. You are searching for a book, you go to the library. If the book is there, you come out with the book. But not every book you want may be in the library. To say the book is not in the library, you have to search the whole thing. Do you search the whole thing? No, you search a catalog. Okay? In those days, we used to have a paper catalog. I'm sure you may remember that. These days, everything is computerized. You kick in, It says, yes, it is in third floor, shelf 47. No, I don't have it. So if the answer is yes in the library search, you get the answer quickly. To say I don't have a book, I must have searched through the entire file. In other words, yes or no answers are not symmetric. It takes more time to say no than to say yes. All of you? That's right. So that the general aspect of search problems. So there are 7 ways. Now, this number of dividing n object into k subset is an integer. In mathematics, they have called this integer as a Stirling number. Stirling. I don't know how many of you have heard of Stirling. Have you heard Stirling for approximation to factorial n? The same story. Come on, guys. If you have done this in physics, factorial n comes as an important factor. So the number of partitions of n objects into k is divided within the curly bracket, and that number is called Stirling number. There are lots of numbers, Ramanujan numbers, Stirling numbers, Fibonacci numbers. These are all infinite sequence of numbers that naturally arise in many aspects of mathematics. So if Tn, so let's look at this now. Tn1, n is anything, k is 1. So Tn1 means what? How many ways in which I can divide n numbers into one subset? There's only one way, put all of them in one. So that's a boundary condition. How many ways in which, so what is T00? That's a boundary condition. You can define it to be either 0 or 1, depending on what your things are. T01 is 0. Tn0 is also 0, so that should be equal here. Now, how does this number Tn varies as I vary n and k? How many with me? So it's a difference equation. It's a difference equation in 2 variables, n and k. How many of you make please? I'm going to give you some quick homework problem for you to do. Let's suppose I have xn is equal to xn minus 1 plus xn minus 2. x1 is 0, x2 is 1. Compute the solution. If x1 is 0, x2 is 1, what is x3? x3 is equal to x2 plus x1, which is 1. What is x4? x3 plus x2, which is equal to 1 plus 1 is equal to 2. What is x5? x5 is equal to x4 plus x3. x3 is 2. x4 is 2, x3 is 1, that is 3. So what does this tell you? Every new number is the sum of the 2 previous numbers. This number sequence is called Fibonacci number sequence. Fibonacci sequence. I'm just giving an idea. How can I rewrite this another way? T of n is equal to T of n minus 1 plus T of n minus 2. So here there is only one parameter. But in here there are 2 parameters, n and k. Just like this Tn can be expressed as a recurrence relation. Recurrence relation means what? I'm trying to define Tn in terms of itself. A Tn for a larger n depends on the value of Tn for a smaller n. All of you may? That's right. That means the present depends on the past. The present depends on the 2 values of the past. That's a difference equation. Difference equation, sequence of numbers, sequence of Fibonacci numbers, sequence of Stirling numbers. It can be shown that T and K is K times T n minus 1K plus T n minus 1K minus 1. That's our current relation. That's how they are defined. And this is, so this means this is Tn1. So Tn1 there are boundary conditions which I have already talked about. So what is the other way of rewriting this? The Stirling number for NCK is K times NC1. This is NC1 minus 1. All of you?
Yes.
That's how the number grows. Now, I would like to be able to show you that this number grows very, very fast. I'm just going to give you an idea. I'm not going to derive. I have given all the derivations in the notes. I'm giving you my entire notes. I'll also go through the notes in little detail. So what is that can be shown? It can be shown that Stirling number T and K, which is given by this, is given by this summation. All of you? In meteorology, probably you don't do these kinds of mathematics. You do other aspects of mathematics, but this is very important in the context of clustering. So what is this? As n grows, this grows in a particular way. So let's look at an example now. 19's n is 19, k is 3. I have 19 objects. I want to divide them into 3 subsets. How many subsets are there? 1.9 times 10 to the power of 8. Follow with me? Coming back, I want you to check these calculations yourself. 19.6 is 6.9 times 10 to the power of 11. That means if I have 19 objects, if I want to be able to divide them into 6 clusters, how many different possible clusters are there? 0.69 into 10 to the power of 12. More than half a trillion. Now let's come to the complexity. You remember? To multiply million by million matrices, I have to perform 10 to the power of 18 multiplication, 18 operation, and that takes 12 days. So how many days are it going to take to generate these numbers? As n is large, as k is large, these numbers are going to be very large. Even assuming I'm able to create these partitions in 1 tick of a clock, how many ticks I need? Exponentially large number of clicks. And to say I have an optimal clustering, I cannot claim optimality unless I check everywhere. Please remember the example I told you. The library says I don't have it until they check everywhere. Are you with me? So that's the complexity issue that I would like you to be aware of. At this time, I want to talk about discrete optimization versus continuous optimization. So what does it mean? Optimization. Why optimization is important? We want best result. An engineer wants to have a best design for an automobile engine. A civil engineer wants to be able to have a best design for a bridge. That's in what sense? My cost must be minimum. Its durability should be maximum. All of you? That's right. That's right. So engineers, any product need design. Engineering, optimality in the design is fundamental. And producing prediction is engineering. What do engineers do? Engineers produce something. What do IMD people do? They produce prediction. Product for public consumption. So the aspect of creating a prediction has an engineering flavor. So I want to get the best prediction possible. Are you there? So the notion of best. So best means optimization, minimum, maximum. I want to minimize the cost. I want to maximize the profit. So optimization can be either in two-way world. One is discrete or continuous. In the continuous world, we use tools for multivariate calculus. So how do I define optimum in continuous variable? The first derivative must be 0. The second derivative must be positive in univariate calculus. In multivariate calculus, what is that? The gradient must be 0. The Hessian must be symmetric and positive definite. Where does it apply? In 4U, I'm trying to minimize the cost function. That's a multivariate cost function. So you compute the gradient of the cost function in 4U. And what is the method you use? That's called a joint technique. A joint technique provides you the method for computing the gradient. Once you compute the gradient, you use the gradient method to be able to seek the minimum. So all the methods that we use traditionally within the 4UR, 3UR community or a problem set are called continuous optimization. Why? The variables take continuous values. But the problem we just talked about, what is the number of ways in which I can classify n object replay clusters? That's discrete. N, there are only n object, there are only k sets. Are you with me? So what is an example of a discrete optimization problem? There are 2 points in the map. I want to be able to find the shortest path to go from point A to point B. That's a discrete optimization problem. Why? The number of distinct paths from point A to point B is finite. Are you with me? You are limited by the existence of roads. So I'm trying to minimize over a finite set of objects. That is discrete optimization. I hope you're with me now. I have an ambulance station, a call for an ambulance comes in. I know the place where the ambulance call came from. I want to be able to go from my station to the place where I'm required in the shortest possible time. So he has to compute the shortest possible time among all possible paths. In a city like Pune, the shortest path may be impassable. In every city in India, it's like that. Are you there? Yes, that's right. So pray the Lord, you never want to have an ambulance service. So I'm now trying to distinguish two kinds of problems. Continuous optimization as opposed to discrete optimization. Where is another example of a discrete optimization? I'm an electrical engineer trying to do the chip design. A chip consists of tens of thousands of transistors. You don't connect all transistors. The transistors are connected in functionality, and you want to be able to connect all the functional units. So what's the question they want to ask? How do I place my functional units within the 2D surface such that the total length of the wire is minimum? Why? The wire are essentially made of gold or silver or platinum because they have high conductivity. IC chips are very expensive. All of you make please? So the chip design, the ambulance driver, aircraft, I want to fly from point A to point B. What is the shortest route by which I can fly? Okay? Those problems are optimization problems. They are called discrete optimization problems. The problem that you solve in Polyvar is a continuous optimization problem. In the discrete optimization problem, there is no notion of a gradient. There is no notion of a derivative. There is no notion of a first derivative, second derivative. Right? In continuous optimization, there is the notion of a derivative, first derivative, second derivative. Necessary and sufficient condition for a minimum is first derivative must vanish. The second derivative must be positive or positive. Are you with me? So many problems in computer science are of discrete optimization type. Many problems in applied sciences are continuous optimization type. Meteorology, especially data assimilation. In modeling, I want to have the best model. Best model in what sense? It tries to capture all the phenomena of the process being modeled. So the best means a good replica of nature. What is the best method for data assimilation? The one that takes least time to be able to fuse data into the model. So the best model, the best and best model, the best algorithm for data assimilation, the best is used in different senses. I want you to be able to apprehend the difference. So these are classical problems. Chip design, scheduling. All of you? Yes. I'm the manager of an aircraft company with 250 aircrafts. Let's take Indigo as an example. I don't have any stock in Indigo, please. Each plane costs you half a billion dollars, 500 million. So every minute you keep them not running, you lose money. So what is the job of the chief design engineer for scheduling? How to minimize that downtime for each plane. Are you in place? The pilots won't work for more than 8 hours, but the plane can work continuously for 24 hours. So you change the crew, but keep the planes flying. So how do I schedule how do you prepare the schedule for the flights such that I can make more money having invested this much money on the aircraft. Are you able to see it?
Yes.
I want you to be able to appreciate that we are not the only one who is solving optimization problems. Many people solve optimization problems. It is better to have a good understanding of what they do, what their problems are, what we do, what our problems are, how they are different. Is there a similarity? If there is a similarity, if there's an idea, can I borrow it here? And that's what science is all about. All of it, so I've exceeded my time. I'm sorry. 1 or 2 minutes. I'll conclude. So what is the topic of the first lecture today? The topic of the first lecture has been the importance of computational time complexity in problem solving, be it in computer science, be it in the aeronautics, be it in meteorology, or be it anything. You've got to be cognizant of the total time. And I told you a method by which you can quantify the time. With that, let me stop. Maybe time for one question. Anyway, after the break, we are going to have the entire class duration for question answering. Any questions? We will meet shortly at 11:30. Thank you. Yeah, please. Please hold on.
Today, there is a dinner arranged at guest house. So people who regularly participated, please join the dinner at 7:30. Director will be there and the program leaders will be there. And I see some people less, so you can convey them also. Some could not make it today. So those who are regularly attending, you probably know it, right? So please convey. You're all welcome.
Two things, free food and be seen by the director.
Correct. That's the way of putting it in an optimal way.
Free food, you can't beat that. And second thing, you got to impress your bosses, namely, we are working, right?
All right. Thank you.
Hey, I'm not going. I'm coming back. Go ahead. You got my note tomorrow.
Yes, that's okay.
My notes.
Yeah, it's in the forever.
ऑटोग्राफ किसको चाहिए? तू दे दे, मैं पूछ लेगा। अरे मेरा किसने साइन किया है?
तो इधर फोटोशूट करवाया है, मतलब वो लॉन्ग तो वैसे भी नहीं मैं नहीं जा रही है पीएचडी में शूट करने। एक स्कूटर है उनका, एक पुराना सा स्कूटर है उसको पेंट करवा। घर का बहुत बुरा हाल है। लोगों ने मेरा नाम सुनाई था, दिखा तो ऐसा हो गया। ये देखो ये जो महल है ये पूरा आप लोगों को कैसे क्या धान को क्या बोलते हैं पूरा ऐसे ये एक्चुअली हमारा घर है और पूरा शमशान वही सोचू रात के ना ना अच्छा तू नहीं पहचान में आ रही है I mean I don't know I can't see any similarity मेरे पे दिख जाता है मेरे सिस्टर में नहीं दिखता है मेरे सिस्टर में एकदम नहीं दिखता है तेरा बैंक का मेरे बाल कितने क्यूट है तू तेरे बिल्कुल मम्मी देख ये फोटो जो है ना ये अल्टीमेट है हाँ सेम आगे की बात ये मम्मी रोटी शायद से मूवी में क्या एक चलो क्या है चाइनीज है हम चाइनीज है ये इंग्लिश को क्या बोलते हैं मराठी चाह चाह चहा पीने चहा संपूर्ण द्यायचा संपूर्ण लवकर आपल्याला तेव्हा शिकवेल म्हणजे ग्रुपमध्ये बसले की ब्रेकमध्ये सुरू व्हायची अशी आता काय करायचं इसको आती है अरे इधर रहती ना 8 साल अरे कौन साइन किए क्या सबने
पता नहीं सर भी क्या हाँ सब कर लिया है कुछ लोग एब्सेंट है
शुभ ज्योति की नहीं
एब्सेंट
नहीं है क्या वो
मुझे नहीं पता शायद नहीं है क्या है पता
आज बहुत ही कम है
नहीं
कम है आज
आपने देखे आधे लोग आए
ये कुछ लोग क्या साइन नहीं करते क्या इधर रोज
यहाँ पे पास नहीं करते ना एक दूसरे को साइन करके रख लेते
हाँ ऐसा नहीं ना करना चाहिए पास कर तो साइन करेंगे ना सब
भूल जाते याद नहीं रहते
हाँ और चाय के टाइम बाहर चले जाते हैं और फिनिश होने के बाद डायरेक्टली बाहर ये अटेंडेंस लेके आ आपका होने के बाद मुझे दे दो
ठीक है
काय नाही का?
मैं बोल दिया मैंने कह दिया कि सर मुझे आपके अंदर काम करना चाहिए हाँ जी सर ये मतलब उसने काम किया है ना इंटीग्रेटेड है पता नहीं अब उससे पहले उसने जो प्रेजेंटेशन किया उसको देख के लगा हमारा किसी के साथ वैसे करता है प्रशांत
No, I don't have. That's a, yeah, it's so. I wasn't speaking that the same years I did. That's my English. Downstairs, I'm doing downstairs. Not in land. Doing downstairs. No,
We can close. Oh, I'm sorry. I'll use it for a few minutes and then.
No,
Shall we start? Welcome back. Welcome back to the last session for this week. I want to read this and This set of notes were developed to introduce the researchers in meteorology to the tools and techniques of clustering methods. I wish to record my sincere thanks to Storm Prediction Center in Norman, Oklahoma for arranging these lectures. We greatly benefited by collaborative work with PhD students Ahmed, Yusuf, and Baldwin, and a colleague, Dr. Spencer. You have seen 3 papers with all these people. So in Norman, we have School of Meteorology, National Severe Storms Lab, Storm Prediction Center, Advanced Radar Center, Research Center. So we have a lot of outfits related to various aspects of meteorological studies. They largely do mesoscale modeling. And then there is a center called CAPS, Center for Advanced Prediction Systems. So CAPS, NSSL, SPC, and the Radar Research Center. I work in computer science, and I work very closely with folks there. So they wanted me to introduce this quite some time ago. I'll show you the first page. It was done in 2012. Actually, I gave the seminars in 2011, and I had handwritten notes. Then I asked the student to give me typed all these things. I have the slides, 110 plus slides in color. These notes, the 3 papers, and several other slides for the seminars that I have utilized. All of these things are available. If anybody wants to contact me, you can always contact me at varahan@ou.edu. OU for University of Oklahoma, all lowercase. I'll be delighted to continue to talk to you. So with that, let me open the floor for discussion. You go first, because she has been asking me questions about some Bayesian things. So please talk loudly so that others can hear and take it.
I little bit want to know about Bayesian method, how to forward the model use in Bayesian method to prepare the flags form. And how it is used. What is the basic theory, in the Bayesian model?
Your question is loaded. She said model. She said Bayesian. What other things?
And the output of the Bayesian that is in the form of flags.
There are so many things. The multi-level is a course in itself. The title of the course.
And
so you all know model. I'm not going to talk about it. You all know output. I'm not going to talk about it. How many of you have known of Bayesian? Come on, guys. How many of you have taken a course in probability theory? Have you heard Bayes rules in probability theory? How many of you know that? Raise your hand. You say, come on. So Bayes rule is a rule in probability theory. Any argument that derived out of Bayesian rule is called Bayesian approach. Are you with me? TDR is an example of a Bayesian approach. ODR can be made into a kind of a Bayesian-based approach. Kalman filtering is essentially an example of a Bayesian-based approach. So many of the things that we do in meteorology are inherently Bayesian. So why is that to be for something to be Bayesian? That's the question. If you understand that, you will be able to understand everything else. Okay. She talked about models, she talked about Bayesian models, and so on and so forth. The important is you need to understand what is Bayesian. So what is the fundamental philosophy in Bayesian rule is the following. So let's take an example. When did moon landing take place? 1966. That's right. So before 1967, when the moon landing took place, did we know how to answer the question, was there life in the moon? It is not. You can only guess. So, before we went to the moon and observed the forms of life, we of the Earth had some ideas about what could happen in the moon. Whatever idea you may have had is based on whatever you know about the planetary systems. So that's called prior information. So prior is something that you have formed an opinion about an event before you know the details of the event. You register for the course. You register for the course thinking that is going to be useful. So what is the prior knowledge when you register for a course? I believe this course will be useful. That's the prior knowledge. Courses are two types, one core course and electric course. Electric course, they are necessary evils, you have to take. I'm sorry, core courses, they are necessary evils, you have to take it. The electives, you choose. Why do you choose an elective? Because you think by taking that course, it will help you to do what you want to do better. That's the prior knowledge. Then the course happens. Then at the end of the course, you say, gee, I thought I will learn all these things, I did not. I thought I will learn this, I have learned everything, I'm ready. So you revise. So before you came into the game, you talk about prior. Same thing about movies. You see hypes about movies, right? Based on the hypes, you expect so many things. Then you spend 1,000 rupees and get a ticket for the first show, you go at the end of the show. Totally disappointed. Didn't you? Yes. How many times that happened to you? Come on, guys, it happens more often than not, you may want to admit. Because you have spent 1,000 rupees and you don't want to tell others you wasted the 1,000 rupees to others, so you want to have a master pay. Oh God, it's a great movie. Don't you say that? So before you watch the movie, based on that assessment, you have a prior information about the movie. You go and watch the movie, then you revise. Good, bad, ugly. Don't you say that? Your movie is good, bad, ugly. That's Bayesian. So what are the two components to Bayesian? You have prior information before the game is played. You play the game. While playing the game, you have observations. Observations provide truth about nature. Prior is your thought about what nature is going to be behaving. I want to combine the two to get what's called posterior. So prior, observation, posterior. Posterior is after. Prior is before. After, before what? After taking the observation. So observation comes in the middle. Prior is before, posterior is after. So I had information, I have my expectations about the movie before. I have revised my feelings about the movie after and go viewing the movie. Are you with me now? That's the fundamental thing. So Bayesian always implies combining two pieces of information, prior with observation. You remember I told you yesterday an example. I had an unknown x. I have two pieces of information, x1 and x2. I want to be able to estimate the unknown as a linear combination of the two. I want the estimate to be unbiased. A plus b equal to 1. B is 1 minus a. So I have a new version of the estimate. Then I computed the variance. I minimized the variance. I got the best estimate. All of it in the place? Yes. So in here, what is x1? X1 could be prior. What is x2? X2 could be observation. I'm trying to combine the two to get the posterior. Are you with me now? Is it ringing the bell for you? All of you? Yes. And that's exactly what life is all about. I thought I want to get a doctorate. I joined the program. I find it too dull. I don't think it's for me. Just get out after first year. I don't want you to do that. Please do. Please continue. There are people who have done that, right? I thought I want to be a lawyer. I do the first year lawyer. No, lawyer doesn't suit me. I want to come to engineering. Don't we do that, please? That's right. No, not you, not you. Don't me. I said not you, me. Gentlemen. We all have, first we have expectations. We make our choices. Based on the experience, either you continue or abort. So everything that we do in life is basic. You go to a restaurant, You have not gone for the at all. You read the reviews. You go and eat. That day is awful. That day it was great. But man, you realize. So you come into the game with an idea. You play the game. And then you revise your concept of the game, the concept of the thoughts about the person. So in probability theory, this aspect is called Bayesian rule or Bayesian method of decision. So there is a random variable X. Before I did anything, I have a information about that. That's called prior distribution. Px, X is a random variable. Is there life on the moon? If you ask 10 people, there'll be 10 different opinions. Each opinion contributes to the probability distribution. Then moon landing took place, thanks to NASA. Now, what is that? Have you answered the question, is there life in the moon? Looking at the flow patterns that are revealed by the sand, it looks like there must have been water. Are you with me? And water is very much needed for existence of any form of life. So is there life on Mars? Is there life on Moon? Is there life on Jupiter? These are simple questions for which we all have prior information. We send probes, then we revise some information, we have a better knowledge. Now what are we talking about? Developing colonies in the moon. Will it happen? God knows. We may not be here. It may take centuries. All of it may. Good guys.
Yes.
So X is a random variable. X is unknown. I have a prior information about the unknown. Then I'm going to have observations about, that is Z. I'm going to have what's called conditional distribution, which is PZ given X. X itself is a random variable. X varies according to this probability distribution. So this is called conditional distribution. So given these two pieces of information, look at that now. This is about X. This is about Z that depends on X. So this reveals information about X, but indirectly. All of it, please. I want to be able to combine the two. So what is that we want? We want to be able to compute the joint distribution of P, X, and Z. X is a random variable, Z is a random variable. They are correlated because Z depends on X. So I can think of a combined distribution. What does probability theory tells you? This can be written as Px times Pz given X. That can also be written as Pz times Px given Z. There are two ways of factoring that. How many of you have me?
Yes.
This is the fact that comes from probability theory. Again, as I always tell, when you are doing any analysis, you must be able to associate which is what. Is this fact coming from meteorology? Is this fact coming from oceanography? Is this fact coming from matrix theory? Is this fact coming from probability theory? So on and so forth. You need to be able to attribute why this is taking place. Okay? So here, there is no meteorology, nothing. It's all pure probability theory. Now these two are equal. So therefore, I can now equate these two. So Px given Z is equal to Px Pz of X divided by Pz. Hey, everybody with me? So what is this called? This is the distribution of X given Z, that's posterior. Given X, this is prior. So Bayes' rule tells you how the prior is transformed to posterior. It's a transformation. The transformation is defined through the conditional distribution.
Numerator, actually. Numerator, is it PXZ?
PZ is the probability of observation by itself. So what is PZ? PZ is equal to integral PXZ dx from minus infinity to plus infinity. I'm integrating x. So this is a joint density. In a joint density, if I integrate one of the variables from minus infinity to plus infinity, what do I get? That's called the marginal distribution. So this is joint density. This is the projection. So this is called marginal density. Marginal density, joint density, conditional distribution, higher distribution. I hope you are familiar with all the terms. Prior distribution, conditional distribution, joint density, marginal density. So you could have written this as P of x times P of z of x divided by integral minus infinity to plus infinity. What is P of z? P of z is this. That's another way of writing it. All with me? Just like you will not eat anything without knowing what it is you are putting in your mouth. Don't do anything without understanding why and how. Are you with me, please? Yes. Why? These are the questions they will ask you in the oral exam. You may have published a paper, but you are not able to understand and explain the contents of your own paper. You got a sorry figure, right? That's okay. They will still give you the degree because they know you. But when you go to get a job, they will ask you. So how is the job interview takes place for PhD and non-PhDs? For a non-PhD, they will sit in front of each other and talk. For a PhD, the only way to do the interview is lecture. With me? All the jobs for PhDs are through lectures. And what did they ask you to do? Tell me what you did. I'm going to give you 45 minutes. Please tell me what you did. All of me, please. So you need to be able to convey the fundamental principles of your own work and related work very elegantly. Then you got the job. And that's the reason we are doing what we are doing, right? We all want to make money. Is there anybody who is not in that category? Maybe then your grandfather is probably ultra rich. You just came here to do a PhD just for the fun of it. Well, I have to make my living. That's why I did PhD. All of you? Is Basin clear, ma'am? Any question follow up?
Practically,
what do you mean by practically? I'm not talking about theoretically. It's practically. This. I want you to avoid this. The best practice comes out of good theory. Come on, guys. Don't think I'm not doing practice. I'm an engineer. I'm not a mathematician. So to say practically is a cover. Come out. Don't hide. I'm not talking to you. That's right. This is the practice. I want you to go in steps. You want to talk about your model. You are worried about what you want to do for your PhD day after tomorrow. That's right. But you have to build. That's where the basin comes in. All of you? Yes. That is how many of you know my book on dynamic data assimilation? Come on, guys, you got to do this. You got to know this book. not only because it is mine, but it's a comprehensive book. It's a book we developed over a period of 15 years teaching at the University of Oklahoma, from 1990 to 2006. We wrote several different versions. And I have a 40 sequence of lectures, 1 hour lecture in NPTEL. The sequence of lectures in NPTEL plus the book together will give you more than you need. I'm not telling you don't do the other things, but that's a place to start. We have several chapters devoted to Bayesian formulation. So I would like to, I want to see hear your practical question. But my suggestion to you is, please read through fundamental books. Are you with me? Yes. You always help yourself. You always. Continue now, please. So what's the follow-up question? I'm not trying to shut you up. Yeah. So let me give you an example of a 3D one, and then say how is related to this. Maybe that's what she's looking for, practical, right? That's right. When you say practice, they will say, what is the theory? When you say theory, no, what's the practice? Are you with me? Please understand, the best practice comes out of the good theory. There is no substitute for good theory. Are you with me? Einstein proved light bends. They proved it later. They proved that light bends during a solar eclipse. Are you with me? Yes. That's right. So your best friend is a good theory. Your best friend is a good theory. So let's talk about the so-called 3D one. So I want to be able to predict a time k. I have, from the previous knowledge, I have what's called the background information, which we call XB. I have a background covariance, which is B, a little b. So what is background? Background represents my prior knowledge. How did I get my prior knowledge? About the movie, the prior knowledge you get by reading the reviews. So how do you get the prior knowledge about the life in the moon? By talking to people, astronomers, and reading things. How do I get the prior knowledge about the weather? It could be a climatology. If you go to Google, the Google tells you what is going to be the weather on a given day. They give you the almanac for the past 100 years. That's what almanacs are all about. What is almanac? Climatology. So what is that to expect? I would expect climatology first. Are you with me? Yes. So if you did not know anything, if somebody asks you what the weather is going to be, you'll say, give me 2 minutes, I'll go to Google and tell you. I'll go to Almanac and tell you. So Almanac tells you 100 years of average of the weather tomorrow. What is tomorrow? February 11th. So what is the weather for the past 100 years, February 11th? They take the average, they tell the distribution, and that's what you can likely expect. Let me give you another example. You are planning a travel in December to Australia. You want to decide what kind of a dress I should take. What do? What's the average temperature in Melbourne during Christmas time in Melbourne? Wow, Southern Hemisphere, December is getting warmer. Put off your sweaters, take some short sleeves and shorts. Are you with me? Is that what you do? Climatology. So climatology is the background. Climatology is the prior. Then observation comes in. Observation has a covariance Z. I want to combine the two. So how do I do that? Let X be the new state I want to be able to estimate. So there is a state X that is unknown. I want to be able to estimate this based on the prior and the new observation. So X minus XB transpose B inverse X minus XB. What does it mean? I have the estimate X. It differs from my background. This is the error. This is the square of the error. It is the weighted sum of squared errors. Plus, I have Z minus H of X transpose R inverse Z minus H of X. This is my observation. This is the forward operator. Everybody should know forward operator, right? The forward operator converts the state into the observation. So H is known, B is known, XB is known, R is known, Z is known. I want to be able to determine X. So you consider this to be the cost function due to background. You consider this to be the cost function based on the observation. Both of them are functions of X. Is equal to J naught X plus JB of X. X is what I want to determine. I want to determine X such that it minimizes the sum. How many of you have been?
Yes.
How many of you knew this earlier?
Yes.
How many of you have heard of 3D war? You know, you have heard of 3D war. Did you see this formulation?
Yes. Yes.
That's right. Some of you have, some of you may not have. So what is this? It's a basic application. Are you ma'am? It doesn't get any more practical than this.
Okay.
So you go, you think what will be the weather in Melbourne on December 25th. You go there. Oh God, I brought all summer clothes, but it's shivering. Could that happen? Yeah, it has happened to people. The climatology prediction may not hold good on a daily basis. It holds good on an average. Then what is that you do? You come back and then say, don't believe this almanac. I didn't take any winter clothes. Gosh, I was shivering. I was to buy sweaters after having gone to Australia. I was shopping for sweaters instead of enjoying the beach. I thought it was going to be summertime. Don't you say that, please?
Yes.
I hope it doesn't happen to you, but that's basic. There's nothing more practical than this. Arvina? Good. Any follow-up on that? Good, wonderful. Who wants to go next? There was another person who said they wanted to go, a lady. I don't see her, but maybe she'll come. Go ahead, sir.
And following this, the inverse problem,
Ah.
like data assimilation is an inverse problem.
That's right. You're the one who asked me about the question
Yeah.
earlier? Okay, good. Now I got it. Thank you.
It is just I asked because the following.
That's sure. Good. Complete the question.
How come the data assimilation is in inverse?
How come your data assimilation is inverse?
Inverse problem.
Okay, good. Now, every estimation is an inverse problem. I'll give you an example for you to have an aha, and then we'll come on. Okay. So what is the question on the floor? How come data assimilation is an inverse problem? You know that problem, do you? What do you think? No, I'm not trying to ask a question to get a cheap laugh. But it's a serious question, you got to understand that. Are you with me?
Yes.
What's a direct problem?
Direct problem.
What's an example of a direct problem? I have a differential equation. I want to be able to solve the differential equation given initial condition.
Yeah.
You learn methods in the theory of differential equation. So once you apply the method, you get a solution, and then you can plot the solution. The solution to the model is called the forecast. So prediction is a forward problem. To do prediction, I need to know the model, I need to know the boundary condition, I need to know the initial condition, I need to know the value of the parameters. If you give me everything, I can create a prediction. Some models can be solved in closed form. Most of the models cannot be solved in closed form. If a model cannot be solved in closed form, what do? You numerically compute the solution. So every model code that solves the model equation using numerical finite difference approximation is followed. Again, did you see this head? I'm not trying to.
No, it's just
You got it. Are you with me? So to talk about the inverse problem, you should know what a direct problem is. So every model code, if you run, you're solving a forward problem. Why? The model code has a model equation because the initial conditions, the boundary conditions, the parameters, you give everything, the model spits out the solution is called the forecast. So what is an inverse problem? Let me first give you a very simple idea to capture your imagination, and then I'll come back to that. This is one of my favorite examples. Everyone has a basic physics degree here. Do you? Is there a non-physics person here? Silence implies consent, right? So, what is the first experiment you do in physics lab? How to determine the acceleration due to gravity? Sir, with me? How do you do that? Pendulum. So, you take a wire, you have a ball hanging, so there is a lever. So, how does the experiment looks like? There's a hook. The pendulum wire comes like this. There's the ball. This is side view. You pull it. So you decide the length. And then you have a stopwatch. You let it go 10 times. You do the stopwatch. So for a given length, so what is that you do? You are going to get a table. L, T. So L1, T1, L2, T2, LM, TM. I'm going to repeat the experiment M times. Each time vary the length. Each time for a given length, I'm going to find the average period. The average period is computed as an average of 10 oscillations. Because if I do one, I may make a mistake. If I do 10, my error is small. Everybody understand? Yes. So T1, T2, TM are the M average periods. Now, what is the formula we know? The formula we know is T is equal to 1 over 2 pi square root of that. Sorry, L over G. Are you with me?
Yes.
This is an inverse problem, sir. I know T, I know L, I don't know G. Look at the way he is nodding, the right way. Keep nodding, let people see. If you give me the length and the gravity, I can compute T. That's a direct problem. That means there is a right-hand side and the left-hand side. If I know all the quantities on the right-hand side, I can compute the value of the left-hand side by simply plugging it in. Just that problem. I know something in the left-hand side, I know something in the right-hand side, there is something I don't know. I have to rewrite the equation. So given L and G, finding T is a direct problem. Given T and L, finding G is an inverse problem. Are you with me? He stopped nodding his head. He said, aha. He said, yes. Say, aha. That's right. Do you see the difference, please? That's an important question. That's why I'm taking time. That's why I'm giving you a simple example. That's why I'm giving you a simple example. So gravity is there. I want to be able to find the gravity. What is the indirect way by which I am going to measure gravity? Using a pendulum. So I have an equation. The left-hand side is the right-hand side. If I know all the quantities on the right-hand side, I can substitute and compute the left-hand side. I know something on the left-hand side, I know something on the right-hand side, but it's something I don't know. It could be, the unknown could be on the left-hand side or the right-hand side. With me? I mean, the knowns are not on one side. The knowns are on both sides. The unknown could be on any side. With me? You always have to capture the ideas from simple, basic parts. Simple, basic ideas. Now let me give you a couple of examples, one or two more examples very quickly. If you give me a matrix, so let's say y is equal to ax. I'm sorry, b is equal to ax. If you give me a and a b, I know the right-hand side. I can compute the b simply by multiplying. Are you with me? That is matrix vector computation. So the right-hand side is known. Left-hand side is equal to plugging the value of the right-hand side. I compute that. Suppose. So known are A and X. Find B. Known B, A, find X. So in this case, what is X? X is equal to A inverse B. Hello? Are you with me, sir? Assuming A is non-singular. Assuming A is non-singular, the solution to the equation Ax is equal to B. A is known, B is known, X is not known. A is left-hand side, B is right-hand side. Everybody? Yes. Now, do you see the difference, please? You should be able to express these things in terms of such simple examples. So how, now coming back to the pendulum problem, what is that? T square is equal to 1 over 4 pi square L over G. Therefore, G is equal to 1 over 4 pi square L by T. All of you? That means G is not proportional to L, is not proportional to T, is proportional to the ratio L by T. Are with me, sir, again? So this is simply a constant. Therefore, what is the solution? How do I solve that? You plot Li versus Ti. You plot Li versus Ti. Or you can compute LITI. L1 T1, L2 T2, Lm Tm. So what do you expect? The product of L and T must be very clearly constant. Why is not exactly constant? Because of measurement errors. You say the length is 2 centimeters, he will say it's 1.998, he will say 2.02. Are you with me? Yes. So up to the accuracy in measurements, if G is constant, the left-hand side must be a constant. The right-hand side depends on the constant times LT. Are you with me? So you find that constant LITR and then plug it into that. Okay? So the first experiment you do in the physics lab, you're solving an inverse problem. Are you there? Any other question?
It's regarding clustering.
Well, louder. I want everybody to hear you.
It's regarding clustering. So we studied clustering in two methods. First is distance method, then variance method. But it's about
First is which method did you say?
distance.
No, it's called hierarchical clustering.
Okay.
Hierarchical clustering, and it's called partitional clustering.
Yeah.
Am I with you?
Yes.
I'm trying to make sure the terminologies are appropriate.
Okay.
And within hierarchical clustering, we did similarity based and then minimum variance based. Go ahead.
But for one,
You said but, right? She didn't say yes. Okay.
yes. So my question is like for one variable, it is fine for me. Like if not one variable, for your example, I'm completely clear about it.
Which variable? Which problem are you talking about?
Like you give an example, like 5 points B, 5 points B2.
5-2. 5-4 or 5-2? Oh, I wanted a two-dimensional space. Oh, yeah, okay, I'm with you. Go ahead.
Example.
But what about we have more variables? Like it is two-dimensional.
Of course. What do you mean by more variable? More variable means the average. More variables is 2.
Yeah.
So, okay, go back. I want to understand your question a little bit further. One second. Let me do that. Sure. So I have a matrix X, please remember that. Now what do you want?
Sir, no, I'll tell about meteorological. I don't know how to explain the mathematical thing.
Okay, explain the meteorological thing.
So I have variables like precipitation, temperature, like humidity, and all these things. So I want to cluster. I want to make few clusters from it, like something happening, some climatological characteristics happening over Western India and Central India.
That's why I did in my honest paper.
Yeah. So I want to.
Okay, you want to know the practical bridge.
Yeah.
The practical bridge.
Not the bridge actually, but I understood like with plots I saw it, but I couldn't.
Okay, good. I'll tell you what. I know exactly where you're coming from. These are standard questions now. Look at this now. You said you come from meteorology, right? Me too. Okay, we talked about it at some length last time. So I have a meteorological model. The model has pressure, temperature, U, V, W, and the humidity H. The model is defined over a domain. The model is an ODE or a PDE or whatever it is. You discretize the model. You have a grid. You have a grid. So in practice, I will say X, Y, T. The pressure at the location XY at the level at the time T. That's a continuous function. But we don't know how to compute with continuous functions. In digital computation, everything has to be discretized. So one way to discretize it is to embed a grid. The grid has nx number of points. It has the ny number of points. The total number of grid points is n is equal to nx, ny. You are going to number them. So I'm going to get a pressure at each of these locations. I'm going to get a pressure vector PT. The vector is a vector of size 1 to n. I'm going to get a pressure vector. I'm going to get a temperature vector. I'm going to get a humidity vector, U vector, V vector, W vector. With me?
Yes, sir.
Then what do you want to do? I want to first be able to cluster the pressure, cluster the temperature, cluster the humidity. Good. Now, the pressure is given at various instances in time. So you are going to give a T1, for example, 6 hours, 12 hours, 24 hours, so every 6 hour interval. So at every hour that is of interest to you, the pressure is a vector. Is it okay? Aha. That's the bridge. That's what you are missing. See, what did he say? I'm interested in clustering pressure temperature. That's right. That's a physical variable. You have to consider the discrete sampled analog of the physical variable for representation digitally. Okay? So Vxyt is a functional representation of pressure whose form you may not know. You are computing that through the model, running the model forward. The model computes the pressure over this grid. So at every time, within the interval delta t, the model spits out the pressure distribution. I'm not interested in every t. I'm interested in 6 hours, 12 hours, 18 hours, and so on. So at the 6th hour, what is the pressure distribution as given by the model solution? Concatenate the whole thing and create a vector. Look at her head. Her oscillation is increasing. Whenever you say, that's a human, when you are in doubt, when you are fully, I know. Your oscillation is a function of your understanding. Keep oscillating your head. Are you with me now?
Yes, sir.
That's right. So you tell me how many times intervals you want to be able to cluster pressure. So my matrix X is going to be the pressure matrix.
Yes.
I'm going to get n instances in time. At each instance in time, I'm going to get m. So instead of m, now what is it I would like you to change? Make it mx, make it my, make it m is equal to mx times my. The row smells the same by whatever name you call. I can call the number of points as mx or nx. So I want to be able to relate this notation with that notation. Now, pressure at time 6, pressure at time 12, pressure at time 72. Can you cluster them? Is that an aha?
Yes.
Can you do this for temperature?
Yeah. So.
Can you do it for you? Can you do it for V? Can you do it for everybody?
Yeah.
Go ahead now.
Okay. So now we cluster for each variable set.
That's right.
So can we cluster this a function of different variables together? It's not.
You can do. So what is that you need to do? You create a new vector. You create a new vector where this is pressure, this is temperature, this is velocity.
Okay.
It will be of length 3m.
Okay.
Ha. So what is the answer? Ha. That's why ha means yes. Are you all me?
Yes.
Is that a practical bridge for you?
Yeah.
Well, one second. I want to make sure that she got it. I don't want to jump. That's time. Sabina,
Yes, sir.
how do you, in other words, pressure is a function.
Yeah, that's true.
Now remember, anything that you want to do in computers has to be digital representation. How did I transform text into digital representation? By the number of words. Why am I mentioning this? I want you to get a general feel for how others do business. If you want to do anything in computers, you need a physical representation of the object. Pressure is an analog device. I want to have a digital representation. How do you get a digital representation from an analog function? Sample. I sample Shakespeare for the number of distribution of words. I sample a program to find out how many words are there. So if you want to automate anything and using computers you want to process, please understand what is the first step. You need to be able to digitally represent the objects in question. Speech, image, fingerprint, text, hyperspectral images, radar images, satellite images. That's the reason my second talk was on where do big data come from? Are you with me?
Yes, sir.
That's right. That's right. So what is the general theme of the second talk was? How do you digitize analog devices into digital representation? That's the bridge. Everybody?
Yes, sir.
And that's exactly what Ahmed paper did, Gusuk paper did. With me?
Yes, sir.
I was talking to my friend during the break. You remember with Baldwin's paper, we had fitted the gamma distribution for rain, for stratiform, for line, for cells, and other things. I want you to ask yourself the following question. India has had monsoon, and Indian monsoon has been recorded right from the days of British time. I don't know how many of you knew this. Indian Meteorology Department was done in 1812 or something. So, whatever number, I forget. But it is the early 19th century. So Indian Meteorology Department, Indian Post Office, Indian Railways, some of the oldest departments known in India. So they have kept recent records. So we should be able to compute the actual probability distribution. What is the probability distribution of rainfall in Bombay during summertime? During Maharashtra in summertime? During India in summertime? Please understand, rain cannot become negative. It's always a positive random variable. Rain distribution, the general model is gamma. Are you with me?
Yes.
I don't know whether somebody has done it, but I do know Rajivan data is available on a smaller grid. To have a greater data as one information, to be able to get a histogram, the probability distribution is something else. Are you with me? You may want to compute alpha beta for Bombay, alpha beta for Maharashtra, alpha beta for some other for some other state. To understand how the rainfall distribution changes from state to state in the same season. Kerala gets rain, Bombay gets rain, Gujarat gets rain. Are you with me? So what is the difference in rainfall in different places? I don't know whether this problem has been solved or not. That's a good problem. We talked about during coffee break. Any other question? Are you done with me?
Yes.
Yeah. No, you are not done with me. You are done with the question. Sorry. Is that wrong? Any other question? We still have 11 minutes. Go ahead, go ahead. Yeah, you wanted to ask a question. I want to finish. Oh, go ahead.
No, deflect.
That's okay, no problem.
Like I have
Louder, I want all of you to
I
hear.
have ensemble data. So like what I want to do is like select few ensembles which are really bad, like bad performing ensembles. And like the main reason is I want like see I'll have generated ensembles for 30 years, 52 ensembles data for 30 years from 1981 to 2010. Now I know how the monsoon rainfall is, and based on the how it's correlated with the observation. I know which ensembles are performing good and which ensembles are not good. But I need to how do my problem is I need to know which ensembles are not going to perform well at the start of my run. So I'll be having so many other variables, temperature, pressure. I need the machine learning or AI to find out what went wrong with the bad.
So he wants the magic. So what did he say? So few years ago, they used to ask the question, can your computer do this? Are you with me? Maybe you have asked that question yourself. Maybe. Can your computer do this? Please understand. If you cannot do it, your computer cannot do it. Computer can only do what you can do, probably in a faster way. Computers can do what you can do. You can solve a smaller problem in a pencil paper, and a computer can solve a larger problem. Are you with me? So what is it he's asking? Is there tools by which he can decide how the future behavior ensemble is decided by the initial behavior? That's the question. But how do you measure the quality of an ensemble? The whole aim of ensemble prediction is to understand the spread in forecast. But you want to say bad ensemble, good ensemble, they want to throw them out. In my book, maybe that's the right one. Why would you throw anything out? Please understand, I told you, in data analysis, throwing data is a crime. You change the data, you go to jail. I'm sorry, nobody's going to put you in jail. But that's the integrity of data analysis. You don't know anything. You run the model. The model gives you your behavior. And you find these things are very large or very small. How do you know? How do you characterize good? How do you characterize bad? One of the aims in ensemble forecast and ensemble analysis is to have an ensemble large enough to see what is the expanse of the state space within which the entire solution can lie. Is it okay, Raha?
Okay, but
Why? Do you understand the premise what I'm talking about? Yeah. I want to understand the forecast covariance. Sir, are you with me? Yes. If the ensembles are close by, the forecast covariance is less. If the ensembles are far away, the forecast covariance is large. That's what we start with, spread. Spread is a measure of the covariance. I want to have a true measure of the covariance. Just because he goes outside, how do you say he's bad? And some days in Bombay, they have, within 24 hours, they have 65 millimeters of rain. Do you say it's bad? Talk to people who live in Bombay. That's a reality. Some days we get 10 millimeters, some days we get 80 millimeters. So what is the range? Range is big. The variance is big. So I want to ask you to reformulate your question. Are you interested in trying to understand the maximum possible variations that can be exhibited by forecast? Or you are always thinking that things all should behave well? You see, you don't have to answer that. I want to think about that. In my view, there are very fundamental reasons for going into forecast ensemble. I have told it a couple of times, I'm going to repeat this. One of the hardest problems in weather forecasting is to forecast the forecast variance. It's to predict the forecast variance. Any error you make in the forecast variance is going to screw up your prediction. Are you with me? Yes. That's right. So what is it you should ask yourself a question? 52 is too small. Maybe you should look for 500 samples. Are you with me? To me, that's that. Don't throw any ensemble out because you have spent money in getting that. Maybe it has information. Your aim should be to get the best estimate of the range where the forecast can lie. For example, it is always true in predictions. That's what's called the cone of uncertainty. I hope you're all, in other words, this is the space in which I'm sampling the initial condition. With me?
Yes.
I run the model. This is T. This goes, this goes, this goes, this goes. Maybe from here it may go here. Maybe it may come here. So you have to ask yourself a question. What is the interval of initial condition you picked that represent the initial uncertainty? You remember? What is the question? How can I discriminate in the early stages? And that is related to the choice of the range of initial condition. Maybe you need to expand this. So what does this expansion tell you? That is the initial uncertainty you have about the initial condition.
Yes.
Then how finely you are going to sample. One of my PhD students did an example with 10,000 ensembles for a 5-variable problem. Why? We just wanted to do it. And that gave us a very good estimate as a forecast errors. But the problem was simple. Why? We wanted to show that how accurately you can measure the forecast covariance. At least on simple problems you should do. At least on simple problems you should do. So the problem could be because you have only 52. The problem could be because your initial range of uncertainty is not representative of what the Mother Nature has initially. So those are the questions you need to ask, not to throw away. There's a tendency to throw things out, right? That's right. You are not off the ground. Your question is a good question to ask. All of it. So there are much more things that can happen. There's many more things that can be affected. The only way to settle that question is probably to ask yourself the question, what is the initial uncertainty and how finely you sample them? To me, a good way to sample Monte Carlo is to finely chop this and take the midpoint of each. You divide it into 500 pieces, 500 subintervals. It chops the midpoint. Then you've got 500 ensembles. Maybe you are doing it randomly. How do you choose the initial ensemble? You are probably choosing randomly. How many of me? Our aim is to understand how the model behaves. I don't have much of an expectations. I want to see the range of possibilities the model can provide. And that's one of the fundamental aims. So we have done some good work in here. We worked on a 5-variable problem with 10,000 ensembles. 5 initial condition, 3 parameters. So the control space was 8-dimensional. We finally chopped the 8-dimensional space over 10,000 ensemble. We learned a lot of things. All of it. Any other question?
So suppose,
Yes.
suppose in those 500 ensembles, maybe 10 or 20 ensembles are very out of the track, then the other ensembles getting a scatter close to them.
Sure.
So then what are the factors that made that ensembles to go?
If I know the answer, I will not be talking to you. I'll be making more money. That depends on the model, sir.
How can we find the factors?
You may have to analyze the model much more deeply. That's what's called sensitivity analysis. How the model solution depends on the initial condition. If I change the initial condition by a small amount, how much the solution changes? That's what you're asking. So in other words, I have a solution. The model solution, x of t, depends on x of t time, it depends on the initial condition, it depends on the boundary condition, it depends on parameters. What is me? Is not B, is B. So what is it you need to do? I need to compute the derivative of that with respect to x naught, derivative of this with respect to xb, the derivative of that with respect to x alpha. These are called forward sensitivities. If the forward sensitivity is small, even larger perturbations in the initial value will not lead to larger variations in the solution. If the sensitivity is large, even a smaller variation in the initial conditions can lead to larger variation in the solution. Are you with me? That's called model sensitivity analysis. We have developed this forward sensitivity analysis. There is a book, I think he told he is going to put it, ask our library to buy. So that is a second book. One is the first one is dynamic data assimilation. Second one is forecast error correction using forward sensitivity method. So please ask that book to be bought by your library so you can gather information about why certain things behave in a particular way and so on. Okay? Fine. I have to go and meet directors at 12:30. Thank you all. I hope you enjoyed as much as I did. I'm going to have a chance to meet you once more during dinner. We will not talk any mathematics. We will talk general things. See you all in the evening. Thank you all. Thank you very much. I appreciate it. Thank you. Director's office in the first floor of the first meeting. Thank you. I will see you in the afternoon.